you're done, which is pretty darn powerful. All right, now there's some properties. Let's talk about some properties of dot products. Properties. It's not very, it's, to be honest with you, up until a couple years ago, I used to do dot product just over and over with students. I've been doing it for years, but I never really understood exactly what it meant. And I would go ask physics instructors, and I never really got a satisfactory answer, the one that satisfied me. And then I started digging around, and I finally understood. Really, you guys, the dot product is a tool of physicists. We use the dot product most in physicists. And what we're looking for is parallel forces. That's what we care about. All right? Did I write force equals, this should, by the way, sorry, I just caught that. That should be work. Right? Force times distance. Okay, so let's talk about some products, or some properties. So W dot V is equal to, well, you can probably guess, V dot W because of the commutative property. In other words, if I do V dot W, don't these guys just switch places? And last time I checked, the products, our products are commutative, which is nothing to it. Now, if we have commutativity, what's wrong with me? If I go, don't think of this as the unit vector, just think of it as another vector named U. If I go U times V plus W, you can probably imagine what happens here. We end up with a distributive property. So this is not times, it's dotting. So if I dot U with the sum of two vectors, I can rewrite this as U dot V, because there's no real multiplication of that. Whoa, that was crazy. It's not U dot, or not U times V, it's U dot V plus U dot W. And that opens up a whole world of prospects for us. All right, now what do you think this one is? What do you think that V dot V is? Well, again, let's just let V equal A, B, okay? So do you agree that if I dot V with itself, isn't that just A squared plus B squared, which is really the square root of A squared plus B squared squared, right? And what do we know that the square root of A squared plus B squared is in terms of vectors? Well, it's the magnitude of V squared. Now that's going to be useful for us when we prove something, which is, actually it's a really, really cool theorem. And then last but not least is, if I dot 0 with any vector, I always get the 0 vector, which makes sense. Can you see how dot product is really the multiplication analog to vectors, if you would? Now, I'm going to show you a little something. This is pretty cool. All right, I think you'll find it interesting. All right, I'm going to do this. I'm going to let, excuse me, I'm going to let this be V, and I'm going to let this be W. Now, if this is V and this is W, what is this vector's name? Can you tell? Remember, the sum of this vector plus this vector equals this vector, because I go tail to tail and head to head, right? So what's this one got to be? It's got to be W minus V. Okay? Now, I want you to think about something for a sec. Can you see where if I have two vectors, it might be really helpful for me to be able to figure out the angle between them? That might be a really useful thing to have out there, because I could have these two vectors floating around in space, right? And remember, vectors are movable, so I can move them so that they're tail to tail, and then if I can figure out what that angle is between, then life gets good. All right? Now, I'm going to use, believe it or not, I'm going to use the law of cosines to figure out a way to determine the angle between any two vectors. Okay, now hopefully you can see this. Think of these, remember, W is a vector, it's a name, it looks like one of these. V is a vector, looks like one of these. W, or one of these, by the way. W minus V is a vector, it looks like one of these guys. If I'm going to use laws of cosines, then I better not think of them as vectors, but I better think of them as their magnitudes, right? Law of cosines is used with lengths of sides of triangles. And I'm using law of cosines because it helps, I've got one angle here, right, which I'm trying to solve for. So watch how this works. I'm going to take the magnitude of W minus V squared, that's just law of cosines, equals the magnitude of W squared plus the magnitude of V squared minus 2, right, times the magnitude of V times the magnitude of W times cosine of theta. Now this is typically when students will go, wait a sec, are we dotting or are we multiplying? It's a great question. we're multiplying because these are just magnitudes. They're not vectors, right? We're using lengths of the sides of a triangle. All right, now, according to this formula, though, right here, we're about to enter into vector land. And watch what happens. According to this, if I take the magnitude of a vector squared, it's the dot product of the vector with itself. So this is W minus V. Ooh, I'm going to need way more room. I'm going to come down here. Pardon my board work here, guys, for a sec. This thing becomes W minus V dotted with W minus V, right? Equals W dotted with itself plus V dotted with itself minus 2 times U dot V cosine of theta. Or, excuse me, I just lied. No, I can't do that. I got a little ahead of myself, got a little anxious. Now notice, there's nothing that says that the product of two magnitudes is their dot product. There's nothing that says that. So I'm going to leave this thing as the magnitude of U, or U, excuse me, W, times the magnitude of V. And then here's my cos theta. Okay? Now watch what happens. This is pretty cool. If we have the distributive property, then we have FOIL. Remember, FOIL is just a generalization of the derivative or of the distributive property. So if I'm going to dot U minus V with itself, what I end up with is, what can you tell? I end up with W dot W, right? Minus, I'm just doing FOIL here, minus 2 W dot V, right? Plus V dot V, which equals W dot W plus V dot V minus 2 times the magnitude of W times the magnitude of V cos theta. Now you can probably see that a couple things are going to happen. Goodbye to W dot W, goodbye to V dot V, right? And what do I end up with? I end up with negative 2WV. I'm going to run out of room. I hate that. Negative 2W dot V is equal to negative 2 times the magnitude of W times the magnitude of V cos theta, which implies, now I'm going to steal some of this space back. If I divide through, that's cos theta by the way, if I divide through by negative 2 times the magnitude of W times the magnitude of V, I end up with, let's change colors so we see this thing brightly. I end up with the cosine of theta is equal to W dot V divided by the magnitude of W times the magnitude of V. I have an equation. I have a theorem. And that's really helpful. Let's kick over a page, rewrite that thing so we've got it written down. All right, I guess technically, if you really wanted to get crazy with it, if you just wanted theta, I know that cos theta is W dot V divided by the magnitude of W times the magnitude of V, right? If I wanted to solve for theta, I could take the inverse cos of both sides and write that up like that. But this is actually pretty useful right here, and here's why. Let's write a question. What happens? Wow, I just had some heavy carbs at lunch, so I may be slipping into a coma. Bear with me. What happens if V and W are parallel? What's that mean? Well, that means I got a vector that looks like that, call that V. I got a vector, well, that looks like that, call that W, and they're parallel, which implies, doesn't that imply that the angle theta has to be 0? True? You agree with that? However, think about what has to happen. Think about what has to happen if that's going to happen. If these things are going to be parallel, if the angle between them is going to be 0, then what does this imply about W dot V over the magnitude of W times the magnitude of V? What's the cosine of theta? It's 1. If two vectors are parallel, that implies that this guy has to be 1, right? Another question, what happens if V and W are, now here comes a physics word, orthogonal. Orthogonal. Now, what does orthogonal mean? Orthogonal means, I'll write it up here, it means perpendicular. Right? Okay, so let's draw an example. I got here's V and here's W. What does that mean about the angle in between them if I move it? Well, it's 90 degrees, right? So doesn't this imply that theta equals 90 degrees? Well, doesn't that imply that the cosine of 90, what's the cosine of 90 again? Oh yeah, it's 0. So really what this means that W dot V divided by magnitude of W times the magnitude of V is equal to 0, which really implies that the dot product between W and V must equal 0, because the denominator doesn't have the ability to make a fraction go to 0. So I can always check to see if two vectors are orthogonal simply by taking their dot product. If their dot product's 0, you've got orthogonality. Remember, that just means perpendicular. Okay? All right. We're going to play with a whole bunch of problems that deal with dot product. And really, dot product is just kind of an interesting way to think about vector problems. It'll be pretty useful. I think you'll like it. All right? I hope to see you tomorrow. Hope you took some decent notes and wrote down a good problem. And we'll talk to you tomorrow. Bye-bye.